Can you see my screen?
Yes.
Okay, good. Okay, so what I'm going to do here is talk about, let's see here. Yeah, talk about some of the S2S forecasting activities going on at Colorado State University. And so I can't take credit for the hard work on any of this. My collaborators here did a lot of the work, including Elizabeth Barnes, Jack Cahill, and Zybeth Carlo Frontera, who are former graduate students, and then current graduate student in my group, Yuchen Sai. So I'm going to talk about three different things here. The first thing I'm going to talk about is a technique we've used that uses machine learning to predict errors in subseasonal North American geopotential height forecasts in GEFS. And so we call this approach errors of opportunity. And so I'm going to spend a lot of time on part one here, showing that certain MJO phases have more predictable errors than others in the GEFS. The second part here is going to look at boreal summer. And so we're going to look at several prototypes of the UFS that show common subseasonal prediction errors over the tropical East Pacific and Atlantic, and show that these errors lead to errors in cyclogenesis prediction in these basins. And then if I have any time, I'll talk about some of the statistical modeling that we've been doing to look at how neural networks might be used to predict Eastern Pacific and Atlantic cyclogenesis. All right, so first of all, let's talk about this approach that we're using to predict errors, forecast errors in GEFS. And so in this first part, we use the global forecasting system, GEFS version 12. And we're looking at reforecasts here from the period 2000 to 2019, where reforecasts were initialized every 7 days. And we're interested in forecasts here at lead times of 10 to 14 days, even though we could look at forecasts out to 35 days as well. And so what we're going to do here is we're going to characterize the forecast into three different classes. One are times where the UFS underestimates geopotential height anomalies over the Northern Hemisphere. Another one is when the forecasts are relatively precise. And then another one where GFS overestimates geopotential height anomalies. And this matrix here basically shows RMS, typical error of UFS, underestimates precise forecasts and overestimates as a function of time of year. And so not surprisingly, fall through spring, you generally see bigger RMS errors than you do during summertime, for example. During this presentation, we're actually going to key in during springtime, where people have shown subseasonal forecasts to be particularly of poor skill, and in particular, we're going to zoom into the Pacific Northwest in a lot of the subsequent results. So as I mentioned, we're going to use a neural network to try to predict errors. And so how this is going to work, and again, I'm not I'm not an AI expert. Many of my collaborators are, but I'm going to talk a little bit about what we've done. So what we're going to do here is we're going to input tropical OLR anomalies as the input layer into the network and run this through a hidden layer of 60 nodes and predict if the UFS either overestimates, gets geopotential height anomalies well, or underestimates geopotential height anomalies. And we could do this for any specific location in the Northern Hemisphere. This particular map here shows a region over Western Kentucky and Tennessee, although as I mentioned, for this talk, we're going to concentrate on the Pacific Northwest for looking at UFS forecasts. Okay, so anyways, this is the results, a first result of using our neural network. And what this shows here is the accuracy of the neural network in predicting H500 errors over North America. And the top row here is summer, and then we go all the way down to spring. Then we have the three classes along here. So we have UFS underestimates, UFS precise forecasts, and UFS overestimates. And the color bar here shows the accuracy. So if the neural network were to have no skill whatsoever in predicting H500 errors, then you would basically have 33% everywhere, which is just, kind of a randomly distributed three classes of forecast estimates. But you can see here that there are some colors on here. Particularly, we're going to concentrate on spring over North America, and that you could see that the neural network, if you input OLR, does have some skill in predicting H500 errors over North America. And these colors here are on the order of 41 to 43%, and even a little bit higher over parts of North America during spring. So this is the bulk properties of how the neural network does. You could also break this down and look at when the neural network is more confident. So in this particular plot, it's like the previous one, but now what we're showing is are the 30% most confident samples, forecasts of errors that were generated from the UFS and from the neural network. And you could see here that the colors have become deeper. And in particular, I want to point out here spring. And so you could see that the neural network has, something approaching 50% accuracy over the Western United States as far as predicting H500 errors in the GEFS model. So that's encouraging. So we're getting, a value that's, greater than 33% and substantially greater than 33%. So now what we're going to look at is we're going to zoom in particular to the Pacific Northwest, and we're going to look at the tropical states that correspond to these confident over predictions from the neural network. And this is what the composite forecast state looks like for the 30% most confident overestimates of the GEFS in the Pacific Northwest. And this is OLR again. And so blue here is negative OLR and red here is positive OLR. So the state that corresponds to the most confident forecast looks like something resembling MJO phase 4. Indeed, if you look at the distribution of MJO phases for these UFS overestimates, you could see that MJO phase 4 pops out. And so that corresponds essentially to enhanced convection over the maritime continent and suppressed convection over the region near the dateline. So this state, is, responsible for producing too high of geopotential heights, relatively predictably over the Pacific Northwest. So what's going on here? So now what we have here are some more composites, and first column here are UFS forecasts. The middle column here are the actual observed state, and the right column here is the error. So basically how much the UFS is over predicting or under predicting the geopotential height. And lead times go down. So we go down from lead times, which are near the forecast initialization, down to lead times of 15 to 17 days. So these periods associated with when the network is very confident at predicting too high of geopotential heights over the Pacific Northwest tend to be associated with UFS forecasts that develop a very, very strong ridge along the west coast of the United States. And if you compare that to what actually occurs in observations, you can see that the observations are much more transient in that you originally get a ridge and then it translates to something that looks like a trough over the Pacific Northwest. So the state of the ridge and trough system is completely opposite in the UFS compared to what you see in observations. So what's going on here? So let's look at the evolution of tropical OLR anomalies. And as I mentioned before, the UFS is initialized in a state that looks like MJO phase 4. So it has, suppressed enhanced convection over the maritime continent and suppressed convection near the dateline. So what happens here in UFS is that the convection anomalies in this initial state don't really change too much. They actually maintain their strength throughout the entire forecast, going down to 2 weeks out. And maybe they drift very, very slowly off towards the east, but they tend to maintain their strength at the very least. Whereas if you look at observations, the observed tropical convective state is much more transient and tends to be associated with weaker convection anomalies that tend to propagate off towards the east much more rapidly. So what's happening is that the UFS is locking into this really strong, convective dipole over the maritime continent relative to, the dateline that looks like MJO phase 4, and it doesn't really translate very rapidly. And so the result of that is it tends to develop a very strong ridge over the western United States. We looked at whether or not ENSO had anything to do with this, because this convective pattern looks like La Nina, and in fact it doesn't. There's no preference for a particular ENSO state, within these most confident samples. So it seems to be dominated by the MJO. So anyways, it looks like the MJO in this model maintains its strength too long and propagates off towards the east too slowly, which is responsible for these West Coast geopotential height anomaly errors. And we have the results of this located in a paper that was just revised for weather and forecasting. Jack actually sent it in yesterday. It was revised after some modest revisions. And so hopefully this will come out soon so you can read more details about it. Okay, so let's switch gears to boreal summertime, and we'll see some commonalities actually with some of the results that we saw during boreal winter. So many of you may know that the Madden-Julian oscillation causes a strong modulation of tropical cyclones in the eastern Pacific during boreal summer. And so this is a breakdown of TC genesis events as a function of MJO phase, and you could see that MJO phases 1 through 2 and also phase 8 tend to be associated with enhanced cyclogenesis relative to other phases. So we wanted to look at, how does the UFS, predict tropical cyclogenesis at subseasonal timescales, and can it get at 2 to 3 week lead times, this modulation of TC genesis, which might have some forecast applications for folks in Central America and Mexico, for example. So we looked at 4 different UFS prototypes, and the reforecast period for this is April 2011 to March 2018. And we're going to look at the ability of UFS to forecast conditions associated with cyclogenesis in the Eastern Pacific at subseasonal timescales. And we're going to use the RMM index of Wheeler and Hendon to diagnose what the initial MJO state is, much like we did for the GEFS results that I showed before. And so I have a couple of composites on here, and you'll note some commonalities for the point I just made for boreal winter. And so what we have here are a Hofmüller diagram of longitude on the x-axis and forecast day on the y-axis when the MJO starts in phases 1 or 8. So we average phases 1 and 8 together and plot the precipitation anomalies at the initial time, which is phases 1 and 8, and see how the precipitation field associated with those MJO phases evolves in time. And so the UFS forecast here is on the right, and you could see here, very similar to the point I made before, is that when you initialize the MJO with sort of a dipolar-like structure here with suppressed precipitation to the west, to the east, and enhanced precipitation to the west, UFS tends to have a precipitation anomaly with the MJO that moves very, very slowly off towards the east and tends to maintain its strength. And one interesting thing about this behavior in UFS is that it tends to lock in this, especially in the subseasonal range of this forecast, into a bit of a dipolar-like pattern where you get enhanced precipitation near the maritime continent in the Western Pacific and suppress precipitation over the Eastern Pacific. So you get this, kind of dipolar-like pattern that kind of locks in, with UFS. Era 5 looks much more transient, and the initial MJO anomaly, not only moves more quickly off towards the east, but it tends to die as far as amplitude. You see this with other phases as well. So for example, UFS in phases 6 and 7 tends to move the MJO very slowly off towards the east, where it tends to be a bit more transient in Era 5. So this sort of behavior, would be expected to produce some sub-seasonal cyclogenesis problems when, in the Eastern Pacific, where we show that the MJO has a big influence. And so we looked at this. And so one of the ways we've looked at this is to look at a genesis potential index that was developed by Moon et al. And basically what this does is it takes anomalies, intraseasonal anomalies, and in omega 500, relative vorticity and vertical shear, that are presumably associated with intraseasonal variability, and plugs these into this, empirically derived formula to determine an intraseasonal anomaly in cyclogenesis potential. And we input large-scale fields associated with UFS forecasts, input those into this index, and compare those to similar results from the actual observed state. And this is the result of that here for phases 1 and 8 on the upper left. And so basically on the x-axis, we have forecast days. And on the y-axis, we have anomalies in intraseasonal genesis potential. The bars on here are a little bit complicated, so let me talk through these. Each of the UFS prototypes is listed here in a different tan color. So prototype 5 is listed in this light tan color, and prototype 8 is listed in this sort of olive green color. And we also have the mean of all the prototypes listed in pink. And then the actual intraseasonal genesis potential is listed from Era I in blue. So anyways, if you start from an initial state of MJO phases 1 and 8, what this plot shows you is generally most of the prototypes want to produce a state of relatively strong suppressed cyclogenesis over the Eastern Pacific Ocean at lead times of 10 through 24 days. And this is consistent with that tendency for the MJO to be too strong and move too slowly and produce that suppressed precipitation over the Eastern Tropical Pacific. However, if you look at Era 5, you could see that Era 5 goes towards a state that looks modestly favorable for cyclogenesis. And so this indicates that pretty much every UFS prototype, except for maybe prototype 6, which is interesting. Prototype 6 wants to do something different, but the other UFS prototypes want to too strongly suppress cyclogenesis over the Eastern Pacific, and this has very big consequences for cyclogenesis on subseasonal timescales. Basically the same story, opposite sign for MJO phases 6 and 7. I won't go through that in detail, but very, very similar story. So anyways, I showed some commonalities about boreal winter behavior and boreal summer behavior associated with MJO forecast and consequences for both cyclogenesis and mid-latitude teleconnections associated with a too slow and too strongly maintained MJO from the initial state. So I guess the question is why? So if we want to improve forecast models, then what is going on in the forecast model to produce that sort of a bias. And so we've started to look at this by looking at the vertically integrated moist static energy budget. In particular, people like Allison Wing and Kerry Emanuel developed this technique that looks at the moist static energy variance budget, that uses the variance budget to look at the processes responsible for MJO propagation and MJO maintenance. I'll just talk about MJO maintenance here, which is on the bottom panel. And so each of the terms in the moist static energy budget is listed on the x-axis here. And you'll notice that we have a blue bar, which represents ERA 5, estimate of the moist static energy variance budget, and a UFS estimate of the moist static energy variance budget. And we're using forecast periods of 10 to 24 days when looking at the UFS. And one thing that we noted here that's very interesting is if we look at the term on the right, minus omega d HDP, this is the vertical moist static energy advection, and it indicates that the UFS is associated with a much lower vertical moist static energy advection or discharge of moist static energy advection than is observations. And looking at this a little bit more, this suggests that there are some biases in the vertical structure of convection in the UFS model that are producing too weak of a discharge and helping to maintain MJO convection too strongly into the forecast. So my graduate student, Yu-Chen Tsai, is looking into this in a bit more detail. But hopefully we'll have something more solid to report on, this particular term in a future telecon. And so basically, the MJO strength is being maintained too strongly due to vertical structure biases with convection. Okay, so don't think I have too much more time here, but let me just give one little plug-in to some results that were derived by our former graduate student, Zybeth Carlo Frontera. And she was looking at the E-specific cyclogenesis problem as well, but in a very different way. And so Zybeth is using a neural network with the MJO, ENSO, and environmental predictors input into the neural network to try to predict cyclogenesis at various lead times. And one interesting thing that Zybeth found is that this statistical model has usable forecast skill out, about 4 weeks in advance for the Eastern Pacific and comparable lead times for the Atlantic, and is able to actually beat simpler statistical techniques like linear regression for statistical, forecast in this region. Still cannot beat the ECMWF model, but at least it beats linear methods such as regression. And so don't have too much more time to go into this, but maybe I'll present this at a future telecon, or one of us will present these at a future telecon. And these results are also contained within a paper that we submitted to Weather and Forecasting that was led by Zybeth. So we're not only approaching the subseasonal prediction problem from a dynamical model standpoint, but also looking at AI and other statistical techniques to see how we might improve. Okay, so this will be my last slide. So just some conclusions. So I showed that a neural network model can accurately identify underestimates of spring 2-week geopotential heights in the Pacific Northwest. And MJO phase 4 seems to be a particularly important phase where the network is more confident. And during those phases, there are too slow and too strong MJO convective anomalies that persist throughout the forecast, and that leads to bad MJO teleconnections along the US West Coast. Something I didn't talk about is that we also looked at summertime and the ability of this neural network to predict errors during summertime, and we actually found that phases 1 and 2 and also places like the Great Plains show a really, really big signal. So that's something that's contained within our paper. That's a topic maybe for a future presentation. Secondly, I showed that when the UFS is initiated in MJO phases that have a strong dipole of convection across the maritime continent, this results in substantial Western Hemisphere forecasting errors at subseasonal timescales that can affect tropical cyclogenesis predictions over basins like the Eastern Pacific and North America. A moist static energy budget showed that the vertical structure of convection is likely associated with some of these errors, and the tendency of UFS is to strongly persist the MJO in the initial condition. And then lastly, I just very briefly touched on the fact that you could use a neural network model utilizing the MJO, ENSO, and other indices to successfully predict East-Pacific and Atlantic cyclogenesis with enhanced forecasting skill, not only relative to climatology, but other statistical models that use linear regression. So I think with that, I'll wrap up and say thank you for listening and happy to take any questions.
Great, Eric. Yeah, it was a very great presentation. So anyone, if you have any questions? Again, our discussion document is open to all, so I highly encourage to put any questions, comments, or suggestions in the document. So yeah, I have a quick question because we have about 5 more minutes. So
okay.
Yeah, 20 years ago when I started my graduate school, like a neural network was very popular, and it was even used for hydrologic forecasting as well. So, and then I'm very glad to see like neural network is shown in your presentation, but the aspect is quite different now, like machine learning approach, and we can use GPU and UFS, and also neural network themselves take a lot of computational cost. But is there any prototype study how the neural network is used to simulate over the loop the UFS system to predict the subseasonal prediction system?
Yeah, that's a really good question. This is probably a little bit outside my wheelhouse because I'm not the I'm not the AI expert, and there's probably other folks in the audience who could do a better job of that relative to UFS. But I know that we saw a talk from Dale Duran here at CSU, where he was, looking at the ability of, machine learning techniques to compete with the ECMWF model as far as, 1 to 2 to 3 week forecasts. And he did show that at least in some, in some contexts, the neural network was comparable and showed a lot of promise relative to ECMWF. That's maybe all I'll say, given that the details of the AI are a little bit outside my expertise, but from what I've seen, there's some promise there.
Oh, thank you for your answer. Yeah, again, the discussion document will be available to everybody. So please put your suggestion, question, or comments on it. So if you have any question or not, let me finish